This is the third lecture of the course MTH 204A for section B. In this lecture, we will talk about dihedral groups. The dihedral groups are the groups of symmetries of regular polygons. Let n be a positive integer not less than 3, and by Pn we denote the regular polygon with n sides. For example, when n is 3, then the regular polygon with 3 sides is an equilateral triangle. For n equal to 4, it's a square. For n equal to 5, it's a regular pentagon, and so on. Now we define the meaning of symmetry of a regular polygon. For Pn, a symmetry of Pn means a bijection from Pn to Pn that preserves the distances between any pair of points and maps adjacent vertices to adjacent vertices. For example, let me depict some symmetries for visualization and understanding. So the first symmetry of Pn that we are going to depict is rotation in the clockwise direction by 2 pi by n radians. So in this picture, the regular polygon, the sides of the regular polygon Pn are drawn in yellow, and the vertices are labeled as 1, 2, 3, 4 in a consecutive manner with green. And the initial positions of the vertices on the circumcircle of Pn, those positions are marked by 1, 2, 3, 4 and in white. So initially you see that any ith vertex is in the ith position. Now when we apply the rotation r, which is a rotation by 2 pi by n radians in the clockwise direction, then we can see that the first vertex has been moved to the first vertex has been moved to the second position, the second vertex has been moved to the third position, and on the other end the nth vertex now occupies the first position. So this is how we depict the rotation r, which is a rotation in the clockwise direction by 2 pi by n radians. The next that we are going to depict is a reflection. What we do is we consider the diameter joining the center of the circle of Pn, join the diameter with the first vertex of Pn, and so with respect to this diameter, if we consider the reflection, then we see the following changes are taking place. So first of all, the first vertex, its position will be unchanged, but now the positions of the second vertex and the nth vertex, they are now interchanged. So the second vertex is now at the nth position, and the nth vertex is now in the second position. Similarly for the third vertex and n-1th vertex, and so on. Then we can also depict the composition of this R and rho as R and rho like this. It's also quite easy to see the R inverse is also a rotation. So it is a rotation in the same amount of angle, that is 2 pi by n radians, but the rotation happens in the anti-clockwise direction. Okay, so therefore in R inverse sends the first vertex to the nth place, the second vertex to the first place, and so on. And then we can also consider the composition of this R inverse and rho, and that is depicted here. So one thing we can see clearly from the picture is, so this R rho and rho R inverse, they are going to be same. This is clear from the picture. And let me tell you that this observation is going to play the most crucial role in the subsequent discussions. Okay, so it is intuitively obvious that a symmetry, let's say T of Pn, is completely determined by the following two things. So a symmetry, as I say, the symmetry sends the adjacent vertices to adjacent vertices. So therefore the first vertex will be sent to one of the vertices that is in one of these positions. And since the adjacent vertices are mapped to adjacent vertices, then the second vertex will be adjacent to the place, to the position where the first vertex has been moved. So now there are n positions for the first vertex to go, and once the first vertex is moved, then there are exactly two choices for the second vertex to be relative to the position of the first vertex. So therefore we see that we have exactly, so for first vertex we have n number of choices, and for each choice of the first vertex there are exactly two choices for the second vertex. So thus we have all total 2n number of symmetries. Let me repeat. So a symmetry of Pn is determined completely by two things. The first thing is the position of the first vertex where it will be, and then the position of the second vertex relative to that of the first one. So for the first vertex we have n places to go, and for each such choice for the first vertex there are exactly two choices for the second vertex, right? Because the first and second vertex, when you will apply any symmetry, they will remain consecutive. So thus we see that there are exactly 2n symmetries of Pn, and as a consequence of this intuitively obvious observations which we have made here, it is quite clear that all symmetries of Pn are precisely these. Why so? Since this list consists of 2n number of symmetries, and we have already observed that the total number of symmetries of Pn is 2n, so it's enough to show there is no repetition in this list. That is also quite clear because from here to here there cannot be any repetition, right? And since rho is a bijection, so from here to here there also cannot be any repetition. So the only repetition can happen is as follows, that some power of r will be some power of some other power of r times rho. That can happen, but that would imply that some power of r is equal to rho. But that cannot happen, because if a power of r is not identity, then it cannot fix any of these vertices, whereas rho always fixes the first vertex. Okay, so there is no repetition in the list. So these are all the symmetries of all symmetries of the regular polygon Pn. And furthermore, we have already observed that our rho is going to be rho R inverse. So thus R and rho, they do not commute. However, if we want to they do not commute, but it's not too bad. So if we want to change the order of R and rho, then once we change the order, there automatically R will be replaced by its inverse. So that's what happens here. I hope I made the point clear that R and rho, they do not commute. However, the situation is not too bad. Once you want to flip their order, so then R has to be replaced by R inverse. Okay, once we flip them, then R will be replaced by R inverse. Okay, now let us observe the following, that every symmetry T of Pn induces a unique permutation on 1 up to n, which denoted by sigma t. So a symmetry, it sends vertices to vertices, right? And it's a bijective mapping. So once we look, given a symmetry, once we look at its once you look at its effect on the vertices of the regular polygon Pn, then we see that it induces a unique permutation on those vertices, or equivalently, since we have already labeled the vertices by 1 to up to n in a consecutive manner. So basically, that given a symmetry, we obtain a permutation on this set. For example, so R, if you consider R, what was R? R was the rotation in the clockwise direction by 2 pi by n radians. So let's see the effect, let's see how it moves the vertices of Pn. So the first vertex is being sent to the second, being sent to the second position. The second vertex is being sent to the third position. So first vertex is being sent to the place of the original position of the second vertex, and now the second vertex is being sent to the original position of the third vertex. So therefore, we see sigma r is nothing but this n cycle. What about rho? The rho is also here. If you see that the first vertex is unchanged, and second vertex, second and the nth vertex, they are interchanging their places, and similarly for the third and n-1 vertices. So from this it is clear that sigma rho is nothing but the product of all these transpositions. So these are all these are the product of these transpositions. And I leave the verification to you that we have the following. So for this sigma r and sigma rho, sigma of r rho is sigma of rho r inverse. So basically, what it means, what we are checking is that this relation also is passed at the level of the permutation induced on the vertices. And as a consequence of this, it's also quite easy to see that the permutation induced by r to the power k rho is the same as the permutation induced by rho r to the power minus k. So every year we can see that some power of rho and some power of r, they do not just commute. If you want to flip the order, then the rotation part must be replaced by its inverse. Okay. Let us also observe that this symmetry T of Pn is uniquely determined by sigma T, the associated permutation that it induces on the vertices. So what I mean by this is, if we take two different symmetries of Pn, then the permutations that they are going to induce on the set 1 up to n, or geometrically on the vertices, those permutations will be different, right? So therefore, I mean, in one hand we have different symmetries, and the different symmetries are giving us different permutations, right? So therefore, we can uniquely determine a symmetry by the permutation it induces upon 1 up to n, or geometrically upon the vertices of the regular polygon Pn. Okay, and this assignment, that is like as I said, that T is uniquely determined by the associated and T is uniquely determined by the permutation that it induces. And this assignment is actually coherent in the sense that if we take two symmetries S and T, then the permutation induced by the composition of S and T is same as the permutation obtained by composing the permutations induced by T and S respectively. Okay, so I mean, let me again repeat. So we have seen that each symmetry is giving a unique permutation on the set of vertices, and the symmetry is in fact uniquely determined by the corresponding permutation, and this correspondence is coherent in the sense that it preserves the composition. So in view of all these, it is quite natural and in fact customary. So it's quite natural to think of identifying the symmetries by their corresponding permutations. Okay, so from now on we will identify any symmetry T with the corresponding permutation sigma T, and indeed by abuse of notation we will let T stand for sigma T as well. So what I mean by this is, for example, from now onwards R and rho, these two letters mean this n cycle and this product of transpositions for respectively for us. So from now on we will not we will, as I said, we will denote both the symmetry and the corresponding permutation by the same letter. So from now on by R, I mean this rotation in the clockwise direction by 2 pi by n radians, and the corresponding permutation which is an n cycle. So both by R I will mean both. In fact, since we will be quite algebraic, we can forget the geometric geometric meaning of R. We can simply from now on we can simply consider R as this n cycle and rho as this product of disjoint transpositions. So the point that I want to make is we first started geometrically. So all the symmetries, they are some nice they do have nice geometric meaning. Namely, we see there it's a rotation, it's a reflection, all these. And now for each such symmetry, we see, when we look at its corresponding permutation on 1 up to n, we see an coherent bijective correspondence. So in view of that, from now on we will simply, because though our motivations were geometric, but things are to be done in a formal and algebraic manner. So from now on we would be much more algebraic, and in that spirit what we will do is this n cycle and this product of transpositions will be denoted by R and rho. As I said, that from now on R and rho will mean this and this respectively. Okay, I hope the point is clear. So as I said in the rest of the discussion, in what follows, whenever I will write R and rho, I am actually meaning this and this respectively. So we started with geometry, then we are formalizing things in terms of algebra. So the rotation and reflection that we have seen earlier, now they are being presented by these permutations. Okay, all right. Okay, so we will move on. Here let us recall the notion of a subgroup of a group generated by a given subset S. So for any group G and subset S, the subgroup of G generated by S, which is denoted by this notation, consists of precisely all elements in G of the following form. So what's the meaning of this? So given a set S, we want to define the subgroup generated by that set. So before getting into the general definition, let's look at the very simple case. Let's say if the set is, let's say, singleton, let's say an element A, then what is the subgroup generated by the singleton, or by the equivalently by the element A? So you see that is nothing but that consists of all integral powers of A, namely it is a cyclic subgroup generated by A. So now we are going to generalize that concept. So here S need not be a singleton, S can be any finite set or in fact infinite. So when a subset S is given, then the subgroup generated by S is the collection of precisely all elements of this form. So S1, so here of this form, so here n is a non-negative integer and S1 up to Sn are from S, and epsilon up to epsilon n are either plus 1 or minus 1. So what it means is the subgroup generated by S is the collection of all finite products of the elements from S and their inverses. Okay, so for example, it will be quite clear to you. So the first example of this is when S is singleton, then this is precisely the cyclic group. Now let's say G is odd and S is 1 and root 2, then the subgroup generated by S, which is denoted by this. So as I said, it will be the combination of 1, 2, 1. To combine it will be the, I mean, here since the operation is plus, so it will be all the integral combinations of 1 and root 2. Okay, because yeah, so I mean, look at the definition. So this is by definition is the collection of all finite products of elements from S and their inverses. So here 1, 2 and their inverses are minus 1, minus 2. So all finite sums of 1, 2, minus 1, minus 2, since because of the commutativity, at any typical element will look like this. And of course, these are going to be precisely all the elements. Okay. Similarly, when G is C and S is 1i, then the subgroup generated by S is Zi. So these are called rings of Gaussian. This is called the ring of Gaussian integers. You don't have to bother about the name. So this consists of all complex numbers whose real and imaginary parts are integers. Okay. Then let me give you another example that when n is greater or equal to 3, then if you consider S to be the set of all 3 cycles in An, then the subgroup of An that this collection is going to generate is the An itself. This is what we have. Discussed in the last lecture. And not only so, like if you replace An by Sn and take the same collection that is the collection of all 3 cycles, then the subgroup of even Sn that it generates is exactly An, because these 3 cycles are always inside An. So the subgroup that will generate, namely some product will be 3. I mean, since inverse of a 3 cycle is a 3 cycle, so the subgroup of Sn that this collection S generates will consist of all possible products of 3 cycles, and automatically they will be inside An. Okay. So again, the point I want to make is if we here replace San by Sn, then even though the subgroup generated by this n collection of all n cycles will be the same. And of course we have some trivialities. So if S is empty set, then the subgroup that it will generate is the trivial one. And if S is the whole G, then automatically the subgroup it will generate will be whole of G for any group G. Okay. Now I am going to leave the following 2 exercises to you. So I am sure that most of you have seen this earlier, and at least even if you haven't seen this earlier in this context, but however the spirit is already familiar. You are already familiar with the spirit. So let me again remind you that if we start with an element A in G, then the cyclic subgroup generated by A is the intersection of all subgroups containing A. So in the sense of containment, this is the smallest subgroup of G that contains A, right? So the similar thing happens also in the general situation when S is any arbitrary subset of G, then the subgroup generated by S is the intersection of all subgroups of G containing S, and thus we can regard this subgroup as the smallest subgroup of G containing S. I would like to remind you that here the smallest does not mean that the smallest is not in the sense of having less number of elements, because if the group is infinite and let's say for example if Z is Z and A is 2, then of course if G is Z, then for any n, all n's will be infinite. And in particular this 2z and 4z, though 4z is a subset of 2z, but however 2z and 4z have same number of elements, because in infinite case having same number of elements means there is a bijection between them. So here the word smallest is not in the sense of having less number of elements. It could be the case that like two infinite subgroups, though one is contained in the other, there can be they might have the same cardinality. So here smallest means in the sense of containment. So what this means is if a subgroup of G contains S, then that subgroup must contain this subgroup generated by S as well. Okay, the next thing is also quite important one. So we will see the importance later on. So for the time being, let me just leave it as an exercise which will be important later on. So it says that if you take your field to be the field of rationals, reals or complex numbers, and consider the set of all n by n matrices having determinant 1 over that field F, then when n is greater or equal to 3, this group is generated by all elementary matrices of first type. Okay. Now let's consider the subgroup generated by Rn rho in Sn, because remember that I have declared that from now on for me Rn rho will mean this and that respectively. So from now on Rn rho are inside Sn. So it's legitimate to talk about the subgroup generated by the set consisting of Rn rho. So for simplicity we remove the curly bracket and simply denote that subgroup by this. So this is in the same spirit of the notation reserved for cyclic groups, notation for the cyclic subgroup generated by an element. So yeah. So we now consider this subgroup of Sn when n is at least 3. We do have these relations that r to the power, since r is an n cycle, so r to the power n is 1, and that's going to be the order of r. Similarly, the order of rho is 2, and r and rho, they interact between themselves in this manner. So these relations immediately tells us that every member in this subgroup generated by R and rho has to be necessarily of the form r to the power k rho to the power l, where k runs from 1 up to 0 to n minus 1 and l is 0 or 1. Because in any product of R and rho, so using this relation we can put the r's together on the left, and in the rest we can put all the rows together, and with this since r to the power n is 1, so once we collect all the r's together, so it will be some power of r. Then using this relation we can see that will be r to the power some k. And regarding the rows, so we can always remove even number of rows from the product. So that's how at the end either we will end up with a row or the occurrence of row will not be there. So thus we are completely convinced that in view of these relations, every element in this subgroup will be of this form. And you see that for k we have n choices and for l we have 2 choices. So there are 2n elements of this form, and they are all distinct. So to see they are all distinct, let us take k, r and ls such that r to the power k rho to the power l equal to r to the power small r rho to the power s, and that and this gives us this. Now you see that if s equals to l, then that immediately forces k has to be r, because both k and r are here. So unless this is, I mean, if s equal to l, so this means identity. So any power, so you can like this we can like r to the power k minus r will be identity. So depending upon k and r, if necessary we can take the inverse, and we obtain that r to the power some power here is going to be identity, and that can happen only when the exponent is 0, right? So therefore when s equals to l, then k equals to r follows immediately. But otherwise we will have r to the power k minus r is rho, and let's then multiply both the sides from the left by r. That gives me this. So here we will have this power of r. Now this can be written as r to the power k minus smaller times r, and r to the power k minus smaller is again rho. So thus we get r and rho commute. But earlier we see that this is the relation between r and rho. So therefore it forces that r has to be equal to r inverse, that is the order of r has to be 2, but that's not allowed because n is greater or equal to 3 and r has order n. Okay. So we see that s has to be equal to l, and once s is equal to l, then it immediately forces k to be equal to r. So that's how we obtain that all elements of this form, they are going to be distinct. All right. Now if you look at the argument that we have used to see that all elements of in this list, they are all distinct. If you look at the argument that we have given here, we actually have not ever used here that these elements r and rho are permutations, or they have some concrete description, let's say this or that. We haven't used that. Okay, so this argument can be repeated, and this argument can be, if we repeat this argument verbatim, then we must be able to prove the following general theorem. So let me repeat. So to show the all elements in this list are distinct, the argument that we have provided here, that doesn't use anywhere that r is a rotation, and that doesn't involve that r is a permutation, or it has an explicit description that it's an n cycle, and rho is a reflection which has this explicit description. We have never used that. So what we have done is we have all here and there what we have done is we have used the, I would say, this group theoretic properties, because now they are all inside the group Sn. So therefore it is quite natural to expect that a verbatim repetition of this argument can lead us to a general result. So this is what the context of the following theorem is. This is what the context of the following theorem is. So the theorem says, if G is a group and let's say there are two elements r and small a in G with the following properties. What are the properties? So r is having finite order, and the order of r is which is denoted by n is at least 3. The order of a is 2, and r and a they have this relation, that is ra equal to ar inverse. So if the group G has two elements with these three properties, then the subgroup generated by these two elements will be precisely this collection, and the subgroup will have 2n number of elements, where n is, again let me remind you, the order of this R. The subgroup will have precisely 2n number of elements, and furthermore we can explicitly see the multiplication of any two elements in this subgroup by this. Okay, so the proof of this theorem, I would like to leave it as an exercise. It is just a verbatim repetition of this argument. So it is quite clear that all elements of this type are here. All elements of this type are here in this subgroup. Now, in view of these three relations, it is quite clear that any element here which is going to be a finite product of R's and A's, and these three relations will force that any typical element will look like this. So it is quite clear that this collection, this subgroup consists of precisely all elements of this form, and there are 2n elements in this. There are 2n elements of this form. In order to show the group has order 2n, you have to show that these are all distinct, and this to show they are distinct, you just need to repeat this argument verbatim, and the rest is again immediate from the properties which are assumed. All right. So now we consider the G. So in this theorem so now we let G be as in this theorem, and furthermore we assume that G has order exactly 2n. I repeat, so this theorem says that suppose in a group G, if there are elements R and in the group G there are elements R and A, where R has order n, which is 3. Now if we furthermore assume that the order of the group is exactly twice of the order of R, then certainly G has to be equal to this, right? Let me again repeat. So in this theorem we have a group G and RA with these three properties. If in addition it happens that the order of G is twice of the order of the element R, then we must have the subgroup generated by R and A to be whole of G. And in that case we are going to consider the following map. What is the map? The map is the map is from G to Sn, and it sends R to the power k to the power L to capital R to the power k, rho to the power L, where let me again remind you that R and rho denote these permutations for us. So if it why this map is very natural to consider, because if you see that when we are considering this subgroup R rho, so any typical element is of this form. Okay, so this R has order n, rho has order 2, and this relation enforces any typical element of this has to be of this form. And in G we also see they have the similar, they are looking similar. So in that sense, so in view of that, it's very natural to associate every element in this group G to the corresponding permutation in the subgroup generated by R and rho. Okay, and the way it is defined from the definition, it is clear that this phi is clearly an homomorphism, and because the product of these two elements, any two elements of this form is given by here, and once we replace, basically what we are doing here is replacing this small r by capital R and small a by L, and this replacement does not make any change essentially, because R and rho, they also do have the same property as R, small r and A. So once you consider the product of these two elements here, so the product can be can be the product of two elements, either this will be this or that, and then we see the similar things also happen between their corresponding images because they do have the same property. Okay, so that shows that this map is a homomorphism. And it's also quite easy to see that also obvious that this map is going to be injective because r to the power k rho to the power l, if it turns out to be identity, then k has to be equal to 0 and l has to be equal to, and k and l both has to be equal to 0. So that means this element will be identity here. That means this is this is injective, and so injective homomorphism. And what about image of phi? So image of phi, you see the precisely from the previous discussion that every element in this subgroup will be of this form. So from this, it's also obvious that image of phi is the subgroup of Sn generated by R and rho. Therefore, phi turns out to be an isomorphism in this case. Which case? When the order of the group is exactly twice of the order of this element. So if it happens, then we indeed get an isomorphism between G and the subgroup R rho generated by the subgroup of Sn generated by R and rho. And this of the all this above observations culminate in the following classification theorem. So what does this theorem say? It says that for any natural number not less than 3 up to isomorphism, there is a unique group of order n such that there is a unique group of order n which has two elements R and A with the following 3 properties. So let me again repeat. So it just says that given any natural number greater or equal to 3, there is a up to isomorphism, there is a unique group of order 2n where the following happens, that the group has 2 elements R and A with these 3 properties. So again, let me remind you the meaning of saying this unique up to isomorphism there is unique. The meaning of this phrase is, so any 2 groups with these properties, that is, what are the properties? Having order 2n and having 2 elements, like having 2 elements with this, any 2 groups with these features will be isomorphic. That's what is meant by up to isomorphism, there is a unique group. Okay. So the proof of this theorem is now immediate. So for the existential part, so what we have to show here, you have to show that there is a group of order 2n for any given n such that it consists of 2 elements R and small a with these 3 properties. First we have to show that. That's obvious because already we have observed that inside Sn, the subgroup generated by R and rho, they do have these properties. So the existential part is, there is nothing to say about the existential part anymore. And the uniqueness part is actually we have discussed over here. That is, if a group, if G is a group of order 2n and order 2n having 2 elements R and A with these 3 properties, then we obtain an isomorphism between G and the subgroup of Sn generated by R and rho. So that shows so first we show that R rho is a subgroup, R rho is a group with these features, and then we show that if G is any arbitrary group with these features, then G has to be isomorphic with R rho. That completes the proof of this general theorem, which says that given any n, there is a unique group of order 2n with these properties. Okay, there is a unique group of order n with this property, that is having 2 elements with such that this and that holds. This is since given any n, there is a group and it's unique, so it indeed deserves a name and special notation. So therefore this is the time to make a definition. So for any n greater or equal to 3, the subgroup generated by R and rho of Sn is called the dihedral group of order 2n and denoted by D2n. Let me tell you that there are some authors denote D2n by Dn as well. So the notation for the dihedral group is not uniform. Some authors write Dn to denote the dihedral group of order 2n. Some authors denote directly by D2n. So you have to be careful. But however, the main point is, given any n, this dihedral group is uniquely characterized by the following, that is uniquely characterized by the following, that is the existence of two special elements R and A, such that the order of R is n, order of A is 2, and RA equal to AR inverse. So this is what we have seen in this theorem, that is, this is what we have seen in this theorem. So that is any group of order 2n with these two properties we have, and any two groups of order 2n with this have to be isomorphic. So that is what we here mean, we express by saying uniquely characterized. Okay. Now to make sure that you have understood the essence of this theorem and the true meaning of this phrase uniquely characterized, let me leave an exercise for you. So for any n greater or equal to 3, we denote by Gn the subgroup of complex 2 by 2 matrices, invertible matrices, which are generated by these two matrices, and show that this subgroup Gn is isomorphic to D2n. How to show that? So again, as I remember that D2n is uniquely characterized by this, or more elaborately, we use this theorem that if a group has two elements, if a group of order n has two elements with these three properties, then it has to be isomorphic to D2n. Right? So in order to show Gn is having this proper, Gn is isomorphic to D2n, you have to just show that these two matrices have these properties, and then the isomorphism, the rest is taken care of by this theorem. All right. Now we will move on to some other topic. So the reason for bringing this topic here will be clear in the later part of this lecture. So we are now going to talk about derived subgroups of a group. So if G is a group and X and Y are elements in G, we define the commutator of X and Y, which is denoted by this as this. So like given X and Y, the commutator of X and Y is XY, X inverse, Y inverse. So here I leave the following verifications to you as exercises, that inverse of a commutator is again a commutator, and more importantly, XY is the commutator of X and Y times YX for any X and Y. So what's the meaning of this? So like if we want to know X and Y whether they commute or not, once they commute, then of course the commutator will be identity, right? If they do not commute, then the departure from the commutativity is is given by this commutator. So thus we can interpret the commutator of X and Y as the measurement of the departure from the commutativity. Okay. So if you want to flip, then this is the thing which will. If you want to flip X and Y, then this is the thing which will come up. Okay. This is what we can see here. Okay. And given any group, we consider the all commutators of x and y. I hope the definition of commutator is quite clear to you. So intuitively it stands for the departure from the commutativity. So x, y and y, x, if you want to know whether they are same or not, then they are then the loosely speaking, the difference or the difference is actually signified. So difference is represented by this. So that means it is the departure from the commutativity. Okay. So now let's again talk about the subgroup of G generated by all commutators. So we denote this by G hat G prime, and it is called the commutator subgroup, or the first derived commutator subgroup, or the derived subgroup, or by some author first derived subgroup of G. So since the inverse of a commutator is a commutator as well, so in view of this, it is quite clear that G prime consists of precisely all group elements of the following form. Let me again remind you, given a set, what is the subgroup of that group generated by that set S? This is the all finite products of elements from S, and all finite products of elements from S and their inverses. But here we see that the inverse of a commutator is again a commutator. So thus G prime is the collection of all elements of this form, namely the product of finitely many commutators. And next we observe that if K is any group, and from G to K we have a homomorphism phi, then the image of the commutator x and y under phi will be the commutator of their corresponding images, phi x and phi y respectively. This holds for any x and y in G. So thus you see that under any homomorphism, group homomorphisms, the commutators of G will go to the commutators of K. So that is the image of G hat, the image, sorry, not G hat, image of G prime under phi is a subgroup of K prime. And the equality hold, of course, if G is surjective, because then every commutator of K will be an image of a commutator of G. Okay. Alright, so therefore if we have a onto homomorphism from G to K, then that onto homomorphism maps the commutator subgroup, the first derived subgroup G prime to the first derived subgroup of K, namely K prime. Now let N be a normal subgroup of G, and let small g in capital G. So since N is normal, then for this G, if we consider this map, that is each x is being mapped to Gx G inverse, from the normality it is quite clear that this is going to be an automorphism of N. And then what we have discussed just above immediately yields that under this automorphism, under this automorphism, the derived subgroup of N maps to itself, and therefore since this holds for any G, thus the derived subgroup of N, namely N dash, is invariant under all conjugations by elements from G. In other words, that is exactly same as saying N prime is a normal subgroup of G, right? So this holds for any normal subgroup N of G. In particular, when N is whole of G, we obtain that the derived subgroup here, the derived subgroup G hat, is a normal subgroup of G. I repeat, so the way we see is for any subgroup N, the conjugation from the normality we obtain that the conjugation by a group element G is indeed an automorphism of N, and then the previous discussion applies here and says that under that automorphism N prime maps to itself, and that provides the normality of N prime in G. In particular, when G is equal to whole of N, then we obtain that G prime is a normal subgroup of G. And of course, the factor. So once there is a normal subgroup, it's legitimate to consider the factor group, and it's obvious that the factor group will be normal because for any two typical elements, this is nothing but x, y, x inverse, y inverse bar, and since this is already in G hat, so this will be identity in G. It is identity in G modulo G prime. So therefore we see that this is abelian, and furthermore, if G1 is some abelian group and F is a homomorphism from G to G prime, then it's easy to see that G hat is contained inside the kernel because G1 is abelian. So if we take any commutator from G, and once we apply F to that, we obtain is commutator of Fx and Fy, right? And since G1 is abelian, it has to be identity. So therefore, any commutator is being mapped to identity by F because of G1 is abelian, and therefore we see that G prime has to be included inside the kernel, and this immediately gives us that if N is a normal subgroup and G mod N is abelian, then by considering the quotient map from G to G mod N, by considering the quotient map from G to G mod N, we immediately obtain that G prime is contained inside the normal subgroup N. So thus G prime can be regarded as the smallest normal subgroup of G such that the factor group is abelian. Let me again explain. So we first established that G prime is a normal subgroup of G. Then we see that G modulo G prime is abelian. Then now we see that if N is a normal subgroup such that the corresponding factor group is abelian, then that normal subgroup must contain G prime. So therefore, if from G, if we aim to obtain want to obtain an abelian group by considering a factor group, then we must consider at least this first derived subgroup. So taking the commutators under our consideration, we cannot make an abelian factor group from G. That's what it says. So here also the smallest means in the sense of containment. That is, if you want to have G modulo in abelian, then you cannot consider something smaller than the first derived subgroup. Let me give you some examples of derived subgroups. So if G is abelian, certainly every commutator is trivial, so G prime will be trivial. For n equal to 3, 5, 6, 7 and so on, the commutator subgroup from the derived subgroup of Sn will be An. You see that the 4 is missing here because for 4 you need to do some more work. Therefore, I have put that here in the list of exercises. So having done this and coupling that with this, we see that the commutator subgroup of Sn is always An. For n greater or equal to 5, the commutator subgroup of An is An itself, because the commutator subgroup has to be a normal subgroup of the main group, right? So the An's commutator subgroup is going to be either when n is greater to either trivial or an itself. It cannot be trivial because commutator subgroup is trivial. That means any two elements will commute. Then that means the group will be abelian, but an is a highly non-abelian group. So I mean, for these two examples, we have used the facts that we have proved in the last lecture. That is, when n is greater to 5, then an is simple, and consequently the only normal subgroups of Sn are trivial subgroup, the whole Sn and an. And for n equal to 3, it's though n equal to 3 is a different case, but that's also quite obvious, because like S3 modulo A3 has order 2, so therefore the commutator subgroup of S3 will be contained in A3, but A3 is a cyclic group of order 3. So from that it is clear that the commutator subgroup cannot be a proper subgroup of A3. Okay. Yeah, as I said that for n equal to 4 you need to do some more work. So that's exactly the context, or that's exactly is given in these exercises. Prove that the commutator subgroup of A4 is this group. And I mean, one thing is of course clear that the quotient has order 3. So therefore the commutator subgroup of A4 will be a subgroup of this. And then you have to prove that if you take any subgroup here, then any proper subgroup, of course non-trivial, cannot be a normal subgroup of A4. Yes, so these twos are these twos are for this situation when n equal to 4. Now let's come to the derived subgroups of dihedral groups. So for any n greater or equal to 3, the derived subgroup is the subgroup generated by R square. And the last exercise that we have put here is about it says that when n is greater or equal to 3, the commutator subgroup of SLNF is SLNF itself. All right. We are now going to define the derived subgroups, or the higher derived subgroups. So we are now going to define the higher derived subgroups. So the first derived subgroup already we have defined. Now the second derived subgroup is defined as the derived subgroup of G prime. In fact, by iterating this, we can define a sequence of subgroups of G. We can define a sequence inductively as follows. That is, if we denote the nth term of the sequence by G of n, then G of 1 is this is the first derived subgroup. And if we assume that Gn is defined, then Gn plus 1 is defined as the derived subgroup of Gn. Okay, so that's how, as I said, that from G we first obtain G prime, then we further consider further its derived subgroup, and then we keep on iterating. Then we define a sequence of subgroups. Okay. So for convenience, from now on, instead of putting this dashes, we will simply instead of putting 2 dashes, 3 dashes, so we will rather use this as the indices. Okay. And from the construction display, it's obvious that each Gn is a normal subgroup of G, because again that follows inductively that G prime is a normal subgroup of G. If Gn is also a normal subgroup of G, then its derived subgroup will be again a normal subgroup of G. So this is we have observed here. So in view of this, it's easy to see that all these are like all these Gns are normal subgroup of G. And in fact, the sequence of subgroups that we have defined inductively is a decreasing one. That is, each Gn plus 1 is a subgroup of Gn. Okay, so yeah. Now we make the following definition, that if this sequence after certain finite stage, if this sequence, if the trivial subgroup appears in this sequence, that is in this decreasing sequence, eventually all terms are trivial. If this happens, then we will say that the group G is solvable. Examples, any finite abelian group is, of course, it has to be solvable. Because the first derived subgroup itself will be trivial. For S3, S4, A4, D2N, so all these groups are solvable, because for S3 the first derived subgroup will be A3, then the second derived subgroup will be immediately trivial. For S4 the derived subgroup will be A4, and then A4 the second derived subgroup will be this, and since this is already abelian, the third one will be trivial. For D2N also this is the case, the derived subgroup will be just this, and since this is abelian, the second derived subgroup will be trivial. But when n is greater or equal to 5, then Sn and Ans, they are not going to be solvable, because you see that Sn will be An, and then you further take the second derived subgroup, you will throughout get An. So you're not going to get the trivial one eventually. Okay, so these groups are not solvable. So when n is greater or equal to 5, S and An are not solvable. And from this, that is, if you have done this exercise, which says that the derived subgroups of SL and F for all n greater or equal to 3 is SL and F itself. From this, it is also clear that when n is greater or equal to 3, then this spatial linear groups are not going to be solvable. So it's very natural to ask that what about GL and F? Like, instead of the spatial linear group, if we consider the full general linear group, is that solvable for n greater or equal to 3? And the answer is not immediate, because finding the derived subgroup of GLN is, it requires some work. Okay. And we cannot simply say that the derived subgroup of this will be just SLN. That is not clear, right? So the GLNF, whether GLNF is solvable or not, that requires some work. But however, the following theorem, which is a very general theorem, provides us an answer to this question, and also the generality of the theorem will answer such similar questions for other groups as well. So the theorem says that for any group G, if G is solvable, then every subgroup of G will be solvable, and every factor group of G will also be solvable. And we do have, in a sense, we do have a converse. What it says that if n is such a normal subgroup of G that n and G mod n are solvable, then G has to be solvable. So the first part of the theorem says every subgroup and factor group of a solvable group will be solvable, and the second part says that suppose we can find a suitable subgroup of the group G such that the subgroup and the corresponding factor group both happen to be solvable, then that will force the group itself to be solvable. So before getting into the group, let me make the following remark. So if G and K are groups, and we have a onto homomorphism from G to K, then by first isomorphism theorem, K is isomorphic to some K is isomorphic to G modulo kernel phi. Now if G is solvable, K being isomorphic to G modulo kernel phi, which is solvable, K will be solvable. Okay, because if G is solvable, then any factor group will be solvable. So therefore G modulo ker phi will be solvable. Since K is isomorphic to that, K will also be solvable. Okay, now with the proof of this theorem we will finish this lecture. So before getting into the proof, I think it's the answer of this is quite clear to you. If G and NF would be solvable, then a subgroup, then this subgroup would be solvable, but that's no longer the case. So therefore GL and F cannot be solvable for n greater or equal to 3. So the question for n equal to 2, if you ask the same question for n equal to 2, answering that question is slightly difficult. We will see that later on. For the time being, let's just stick to the case when n is sufficiently large, that is greater or equal to 3. The proof of this theorem is not at all difficult. So first let's prove the first one. If G is solvable, then every subgroup will be solvable, because that's easy to see, because from the definition, any derived subgroup, let's say the nth derived subgroup of H is easily seen to be contained in the nth derived subgroup of G, because any commutator of a subgroup will be a commutator of the bigger group. So from that it is clear, and from the solvability of Gn, this becomes trivial at some point of time, forcing this to be trivial. So therefore we have the desired solvability for H. Now let's prove the solvability of the factor group. So let n be the normal subgroup. Let n be the normal subgroup. Just a minute. No, there is a slight typo. There is a normal subgroup. I will make the correction. We have to show that G modulo n is solvable. So certain it's not assumed that it is solvable. I will make the correction before uploading the PDF. Okay, so we consider a normal subgroup n of G. And to show the solvability of G modulo n, our first observation is that under the quotient map, the n for any n, the nth derived subgroup of G maps to the nth derived subgroup of the quotient group. That is quite obvious, because we can if we go by induction, so if we since the map pi from G to G modulo n is surjective, so the image of G prime will be the image of will be the derived subgroup of G modulo n. Okay. Now then we restrict pi to G prime. So therefore this map the restriction of pi to G prime will be again onto. Then we iterate the same process, that is the derived subgroup of G prime will map to the derived subgroup of G modulo n, derived subgroup of G modulo n prime. So the formal proof goes by induction, assuming that pi of Gn is G modulo n and the nth derived subgroup of G modulo n. From the surjectivity, we immediately obtain that. So from the surjectivity of the restriction of pi to the surjectivity of this restriction of pi from Gn to G modulo nn, we immediately conclude that the derived subgroup of Gn, which is certainly this, maps to the derived subgroup of this group, which is this. So inductively we prove this happens, that under the quotient map, all derived subgroups map to the corresponding derived subgroups of the quotient group. And since G is solvable, so at some point of time this will be trivial, which forces this to be trivial as well. So the solvability of G modulo n is obvious. Now we prove the second part, The second part says that if n and G modulo n both are solvable, so G modulo n is solvable, that means for some k, the k derived subgroup will be trivial. So remember, the identity in G modulo n is n. So now we recall that we have made a general observation here, that is under the quotient map, the derived subgroups maps to the corresponding derived subgroups of G modulo n. So this is nothing but pi of, this is nothing but the image of the k derived subgroup of G, and since the image of this subgroup is just the trivial one, it immediately follows that the subgroup itself has to be contained inside n, okay, because for any x lying here, xn, pi of xn will be n, so that means x has to be inside n. So once this is there, and now we use that n is solvable, so for some m this will be trivial, right? And that immediately forces gk plus m, being a subgroup of n to the power k plus m, the k plus mth derived subgroup will be trivial. So as I said, the proofs are quite straightforward. So that shows that in order to show a group is solvable, if we cannot directly show it's solvable, however, we are able to find a normal subgroup such that the subgroup itself and the corresponding factor group both are solvable, then we will immediately obtain that the given group is also solvable. So this criteria turns out to be very helpful in several situations of proving the solvability of certain groups. Okay, so with that I will finish this lecture.